So we left off on example 4, special cases. So when solving equations, there are 3 outcomes to an equation. There's a solution that's like x equals 2, x equals -3, or even x equals 0. But then there are 2 other types of solutions. The first one is an identity. I'll either write identity or infinite solutions. That just means that basically the left is equal to the right. And then no solution is when the sides aren't balanced. They don't make sense, okay? And that one will be easy to see once we start doing these examples here. So with A here, the first step I'm going to do is I'm going to distribute that 6 into the parentheses. And I have 6x plus 18 equals 6x plus 3. All right, now at this point, some of you can see that they're not balanced, okay? Some of you are that good and you can see it. But let me prove to you that the left is not equal to the right. If I go ahead and try and solve this, I subtract 6x from both sides. Those x's cancel, I'm left with 18. Those x's cancel, and I'm left with 3. So I have 18 equals 3, and that's not true. So that's where my no solution comes into play. The left did not equal the right. But now with B, well, on the right side, there's not much to do. I'm just going to rewrite that. But on the left side, I have to combine my like terms. So 3x minus 6x is -3x. The 11 comes right down. And now you can see I have 2 things that look pretty similar. Okay? I have -3x plus 11 and 11 minus 3x. They both have a -3x and they both have an 11. But if you don't believe me, let's go ahead and solve. Let's add 3x to both sides. These x's cancel. These x's cancel. And I'm left with 11 equals 11, which is true. So this is what we call an identity. Or infinite solutions. Okay? So again, we have 3 types of solutions. We have a solution, which is like x equals a number. We have no solution, where the x's cancel out and the left is not equal to right. We have like an imbalance there. And then we have one where we have the left equals the right, and that's called an identity or infinite solutions. And the reason why we have all of these things is so that I can take information, all right, like in example 5, put it in a model, and then use it to predict. Okay? So let's look at example 5. And this is where math actually is useful in life. And I know Karan has asked this before, and Karan has said, when will we ever use this math? And this is where you use it, Karan. I wouldn't lie to you. This is business, okay? This is like the stock market. This is maybe sales projections over the years. This is what you're driving at in math, is to actually use it in a real world scenario. So the average annual expenditures per student, Y, in dollars for primary and secondary public schools in the United States from 1998 to 2005 can be approximated by the model Y equals 355.3t plus 3,725, where t is between 8 and 15. All right, with t equal 8 corresponding to the year 1998. So according to this model, during which year did the expenditures reach $7,633.30? So Mark, since you didn't sing with me at the start of class, what year makes that true? What year did the expenditures reach $7,633.30?
$7,000. I'm gonna say 11.
11. I would agree with you. But how did you know it was 11 and not say 10?
I don't know. I just kind of winged it. I feel like this is above half, and the other one isn't.
Hey, that's actually a good thing. You approximated, you estimated. So Mark was like, hey, 7,633 is about halfway between 7,000 and 8,000. So Mark did, all right, let me go about halfway, trace that over. Well, that hits this bar, and this bar corresponds to 11. So T equals 11. But here's the thing, Mark. It says which year. So year 11 doesn't make sense, really.
Is it 2011 or?
Not 2011. You're getting close. So let me help you out here, Mark. It says year 8 corresponds to 1998. So down here at the bottom, 8 is 1998. Do you see that?
Yes.
So 9 would be 1999. What would 10 be?
2001.
So 10 would be what year?
No, 11 would be 2001.
2001. Because 10 would be 2000 and 11 would be 2001. So that's your answer. All right, so I can use a graph to predict the data or extrapolate data from it to kind of report out to my people in a business meeting. And what I can see by this graph is I can see that expenditures for student supplies, all right, for primary and secondary public schools is going up over time. It's increasing, okay? And there might be a cause for that. Like right now, things are going down because of what's happening out there, all right? But maybe in these years, there's an increase or an influx in the number of students that are attending primary and secondary schools, causing all of that to go up. Let's look at this one. So let me erase this. This is talking about food. This is something near and dear to my heart, okay? So the annual sales in billions of dollars of food and beverages at full-service restaurants in the United States from 1998 to 2005 can be approximated by the model y equals 6.37 t plus 67.5, where t is between 8 and 15. And the year, or when t equals 8 corresponds to the year 1998. According to this model, in what year were the annual sales about 125 billion? Explain how to answer this question graphically and algebraically. Well, graphically, that's easy. So graphically, I go over here just like Mark did. All right, 125 is going to be right about there. And I'm just going to trace that over. I'm going to see that comes out to be 9. So I get t equals 9. So this is graphically. I got t equals 9. And that corresponded to 1999. Ooh, that looks not good. But, Garrett, it asked me to explain it algebraically. And I don't know if you knew this, but algebra is my middle name. Okay, Garrett? So what I'm going to do here, and hopefully you have a calculator, Garrett, because I'm going to need you to check my math. Okay? Algebraically, Garrett, you there?
Yeah, I'm here.
Got a calculator?
Yeah.
All right, cool. So it gave me this big, long equation right here. So I'm going to write y equals 6.37 t plus 67.5. And what I'm going to do, Garrett, is it told me what y was. It said y was 125 billion. But since everything's in billion, I only have to write 125. And now, Garrett, I need to solve this equation. So how do I go about doing that, Garrett?
You subtract 67.5.
Yeah. Now, can you do 125 minus 67.5 before I can? Is that
Probably.
52.5? No, 57.5?
Wait. Oh yeah, no, 67.5.
Yeah, 125 minus 67.5 is what?
57.5.
Yeah, 57.5. So now I have 57.5 equals 6.37 t. And how do I get rid of that 6.37, Garrett?
You divide.
Divide.
6.37.
Now, I'm good. I'm not that good, but can you tell me what t is about equal to here? Is it about 9?
Yeah, it's like 9.02.
Yeah, it's about 9 years, right?
Yeah.
It's approximately 9 years. So here, notice I got the same answer just about as graphically. And why do I need to be able to do things graphically and algebraically? When you're in a presentation, nobody wants to see an equation, okay? They want to see a nice, pretty graph, okay? So we have a graph because it's pleasing to the eye. But algebraically, that's the beauty in everything, is that allows me to predict what it's going to be like. Now, Alex Emmy,
Hi.
how are you?
I'm all right.
Now, Alex, what do you see? When you look at this graph, what do you see? What is the trend in the data?
I'm looking at, hold on.
Just tell me generally, what do you see? Is it going up? Is it going down?
Every 10 like billions, it's going up.
Oh, it's going up. Would everybody agree with Mr. Annie that every year the spending of food is going up? Sarah, would you agree with that?
Yes.
Now, do you have any idea why it's going up every year? Why might the spending of food be going up? And this is where math comes alive like a magic show. Mr. Kitchen, do you know? This is like your wheelhouse.
Does it cost more? I don't know.
Well, that could be something. Maybe that is something. The
More
cost of
people?
food is going up. I think you might be right there, Mr. Kitchen.
Yeah.
Every year, the cost of food gets more and more expensive, right? Like when I was a young lad, I went to Tom Jones in Brookhaven. Now it's called something different. But you used to be able to get 2 eggs, 2 pieces of bacon, 2 pieces of toast. It was called the Blue Ribbon Special, and it was $2.75, and now it's like $5. So Kitchen, I think you're right. But there's also another cause. Every year, the population on the earth increases, and more people need food, so more people are buying food. Therefore, driving up the cost, just like that. And that's what math is all about, is to look at trends and to kind of take the data and extrapolate and make a prediction. I believe in science it's called like a hypothesis, and then you try to prove that hypothesis. All right, now let's go to the next page. Everybody needs a graphing calculator for this. So I need you guys to follow along. So let me get my work right next to me. So on your graphing calculator, first off, everybody, this is your home screen, okay? And I'm going to clear out all this fun stuff at the bottom for you. So now follow my keystrokes down here if you get lost, or you can listen to my voice. I've been told I have a voice that should narrate the Discovery Channel Earth videos. So here we go. So I have 2 lines in this problem, okay? There are 7x minus 2 and 4x plus 13, and I want to know where they cross. That's why I set them equal to each other. So the problem is 7x minus 2 equals 4x plus 13. And how do I do that without actually solving it by hand? So I come up here to y equals. If you have anything in there, you're just going to clear it out. But you're going to type in 7x minus 2 into the first line. And in the second line, you're going to type in 4x plus 13. And now we're going to hit the graph button. And we can see these 2 lines look like they want to cross, but they don't on my screen. So I can zoom out. So I hit zoom. I can go to number 3, which is zoom out, hit enter, and you can see that my lines cross right about here, telling me that they're going to cross in the first quadrant. So I need to find that point. So I'm going to go to the table. So I hit second graph. And now I'm looking for where this column, y1, is equal to y2. Does anybody see where those 2 columns are equal? When you see when they're equal, just shout it out.
Column 5.
5. So your answer is x equals 5. And what I did is I allowed my calculator to do the work, and I allowed it to solve it graphically. So my answer right here is x equals 5. Now, what I want you guys to do is I want you to answer A, B, C, and D. You can use the graphing calculator method. You could solve it straight up. Or if you know another way, you could do it that way. But I'm going to give you guys a couple minutes to get that done, and then we'll go over it.
What? Okay. Let me get the charger. Hold up.
All right, here we go. Maggie, what'd you get for the first one?
X equals 12.
Yeah, that one was easy, right? I probably would have just multiplied each side by 4. All right, let's go with Ben. What'd you get for the second one? B.
They just changed. I fucking hate it.
Ben?
Still just, you can still do the,
Think you're breaking up. Did everybody get -1?
yeah.
All right, cool. What about Kelsey? What did you get for C?
For D or C?
C, as in,
Oh. I got 2.
you got 2?
Yeah.
Okay. And D, Miss Gregg, what'd you get?
-10.
I got -2 as well. Now, I already told you, if I try to answer this bottom one using the graphing method I just taught you, it's not going to work. All right, it says it right there. It does not appear because it's a decimal. But there's other ways to do it. And no, this is not in your notes, so you have to pay attention. So we go up here and we're going to clear out what we got, and we're going to type it in the same way. So it's 3 times x plus 2 in parentheses, and then we go down and x plus 5. Now we're going to learn about this later this year, but I like to show it as it comes up, and we can kind of learn about it all year instead of just at the end of the year. So now when I graph it, okay, my graph's still messed up, so I'm going to go back to Zoom. I'm going to put it back to where it was, and you can see it crosses right here, okay? And if I go to my table, well, that was in the negatives, so I can see that my one line here passes my other one, but they don't share a number. So how do I use my calculator to do this? Well, I need to calculate the intersection. So I hit second and trace because that's going to get me to calculate. And then I want to know, where do these two lines intersect? So I get on number 5. And this is where you guys might get hung up a little bit. It talks about curves. Curves are just fancy ways of saying lines. So it says first curve. Well, my first curve is the bottom line here. You can see it's blinking on my screen. So I'm just going to click on it just by hitting enter. Now my second curve, you can see it moves to the other line. So I'm going to go ahead and I'm just going to click right around there. Now it asks me to guess. So I'm going to try and put that blinking dot where I think they cross, and I think it's right around there. So I'm going to hit enter. Guess what? It gave me a number. It said x equals -0.5. Okay? So let's see if we were right. Let's see if x is -0.5. So when I go and solve this equation at the bottom, all right, I'm going to distribute that 3 first. And I have 3x plus 6 equals x plus 5. I'm going to go ahead and get all my x's to one side. So I have 2x equals 2x plus 6. Try not to skip steps for you guys. Equals 5. And now I'm going to go ahead and subtract 6 from both sides. And then when I divide by 2, well, look at that. I got x equals -1/2. So I can use my calculator to help me solve these equations when they are decimals.